Welcome. In the previous session, we had looked into simple linear regression, wherein we were given a set of data points, right? Let us say x1, y1, x2, y2, all the way up to x and y1, and we saw how to fit a model y is equal to a0 plus a1 x. So our objective was to find out the values of a0 and a1 such that the model best represents the data point. That is what we had looked into it. That is going to form the basis of this session, right. The outline of this session is going to be under linear regression we are going to discuss multiple linear regression and polynomial regression. So in multiple linear regression we are essentially trying to fit a model y is equal to a0 plus a1 x1 plus a2 x2 plus a3 x3 and so on, let us say till am xm, right, where x1 x2 x3 are the independent variables. So the data points are given like this, x1 x2 x3, and for this, so let us say this is 2 8 9, the y value is given, the dependent variable value let us say 15. So like this we are given n points, right. So our task is to fit a model y is equal to a0 plus a1 x1 plus a2 x2 plus a3 x3. We can either fit this type of model, right, wherein we have a constant coefficient. So we will discuss that first, or our model can also be y is equal to a1 x1 plus a2 x2 plus a3 x3. So here if we see we do not have a constant coefficient. So we will also discuss that case, right. So that is what we are going to do in multiple linear regression. In coming to polynomial regression, in polynomial regression we are required to fit a model y is equal to a0 plus a1 x plus a2 x square plus a3 x cube, right. So in this case the data that is given to us is the independent variable x and y, let us say 2, 8, 5, 3, like this we have been given n points. So our task is to find out the values of a0, a1, a2, a3 such that this model best represents this data points, right. So that is going to be polynomial regression. Again in polynomial regression we can do it with constant coefficient or without constant coefficient, depending upon the need. We can either have a constant coefficient or not, or the constant coefficient may not be there in the model. So that would be an extension of the discussion that we would have till that point of time. So that can be easily handled, right. So in this case what we will be essentially doing in polynomial regression is we will be converting it into a multi linear regression, right. So y is equal to, it is going to be, let us say if we have the constant coefficient a0, then we are going to say plus a1 x1 plus a2 x2 plus a3 x3, where x1 is nothing but the data point x which is given to us, x2 is the data point, each data point squared, so x square, and x3 is going to be x cube, right. So once we do this transformation, right, this is nothing but the multiple linear regression which we will be discussing in the first half of the session, right. So polynomial regression is essentially being converted into multiple linear regression. After that we will be looking into general linear least square model. So this was for simple linear regression. When we do multiple linear regression and polynomial regression, there will be when we do this multiple linear regression or polynomial regression, this coefficient matrix is going to contain lot of terms which need to be evaluated, right. So either we can stick to that process or we can adopt this general linear least square method, wherein from the data points we will be able to directly get this A matrix, right. The coefficient matrix and the right hand side can be easily obtained if we know general linear least square method. Okay. So under general linear least square method we will be discussing multiple linear regression with constant coefficient and also multiple linear regression without constant coefficient. So that is going to be the focus of this session. So in this case whatever we had considered so far, we had only one independent variable, right, one dependent variable and one independent variable. So in multiple linear regression we will have more than one independent variable, the dependent variable is still 1, right. So, we are talking about models like y is equal to a naught plus a1 x1 plus a2 x2 plus a3 x3 and so on. So, now let us look into multiple linear regression, right. So, in multiple linear regression, these two are independent variables x1 and x2, right. So, for example, that can be temperature and pressure. So, these x1 and x2 are independent variables, right, and y is a dependent variable. In this case, the model that we want to fit is the model is a naught plus a1 x1 plus a2 x2. So, this is y model, right. So, there depending upon how accurately this data was measured, there may or may not be an error associated with each data point, right. So, our model is a naught plus a1 x1 plus a2 x2, and our task is to find out the values of a naught, a1 and a2, right. So, this is equation involving two independent variables. So, we can have an equation involving m independent variables. So, for example, we can have y is equal to a naught plus a1 x1 plus a2 x2 all the way up to am xm, right, and since this is the measured value and this is our model, the error vector would be there, right. So, this can be compactly written as a naught plus summation I is equal to 1 to m ai xi. So, that will capture this part completely, right, except for the a naught which we have separated out, and then plus e. So, this is known as multiple linear regression and it has m independent variables. So, first we will look into this case. Once we are comfortable with this case, this is merely an extension of this can be extended to this one, right. So, even in this case we need to define, we need to set a criteria, right. So, the criteria is again going to be the sum of square of errors, right. So, this is the model value, this is the observed value. So, this is the error, right, error associated with the ith point. So, we are going to square it and then we are going to sum it up, right. So, SR indicates the sum of square of the residuals or the sum of square of errors. So, for this again we need to apply the stationary condition. So, here we have three unknowns a naught, a1, a2. Remember x1 I and x2 I are known, right. So, those data points are known. So, we need to differentiate this with respect to a naught, a1 and a2, right. So, when we differentiate this with respect to a naught, right. So, it is 2 times this expression, right, 2 times. So, same thing, x square, differentiation of x square is 2x dx, right, and then the differentiation of a naught with respect to a naught will give us 1, but since we have this minus sign over here, we will get minus 1, that is why this minus is over here. Now, if we expand this, this is minus summation of yi plus a naught, because of this minus and this minus, this will become plus. Similarly, plus a1 x1 I summation plus summation of a2 x2 I, right. So, since a naught, so the summation of a naught is n a naught, and then a1 and a2 can be moved out of the summation, and since yi is known, the data is known. So, summation yi can be calculated. So, we take it to the right hand side. So, this will be a constant term, it does not have any coefficient associated with it. So, we take it to the right hand side, similar to what we did earlier, right. So, now this is a equation, linear equation, right. This term is known, summation x1 I is known, n is known, and summation x2 I is known, right. So, this equation if we see, it is a linear equation in a naught, a1 and a2, those values are not known. So, similarly, we need to do dou SR by dou a1. So, whatever equation we have derived is given over here, right. So, let us calculate dou SR by dou a1 equal to 0, right. So, we apply this stationary point condition, right. So, in this case again 2 times this value. So, this 2 and this should be evident, and then we need to differentiate with respect to a naught, right. So, differentiation of yi will be 0, differentiation with respect to a naught would be 0, differentiation with a2 will be 0. So, differentiation with respect to a1 will give us the coefficient minus x1 I. So, that is why we have this x1 I and this minus over here, right. Similarly, 2 can be eliminated because the right hand side is 0, and then we expand this, right. So, here we have minus summation of yi x1 I plus a naught x1 I plus a1 x1 I square, because this is x1 I and this is also x1 I, right. So, square plus summation of a2 x2 I, a2 x2I and x1I, right. So, in this equation if we see, since x1 is completely known and y is completely known, this term can be calculated, right, and it does not involve any coefficient. So, this can be taken to the right hand side. So, that is why that is what we have here, and similarly a naught can be taken outside over here, summation of x1I plus a1 which is unknown, a1 summation of x1I the whole square plus a2 summation of x1I x2I. So, this equation is again a linear equation in a naught a1 a2 and a naught a1 a2 are unknown. So, that is our second equation. Similarly, we can do dou SR by dou A2 equal to 0, right. I leave the differentiation to you, right. So, here also we will get equation which involves a naught a1 a2, they are linear. The right hand side is summation of yi x2I, right, and all these coefficients can be calculated. Since x1 x2 is known, these things can be calculated, right. So, now we have 3 equations in 3 unknowns. The unknowns are a naught, a1, a2. All the other terms can be determined from the data itself, right. So, these 3 equations, since they are linear equations, we can put them in the conventional form, right. So, the first equation n is known. So, it comes into the coefficient matrix, right. This is our coefficient matrix, this is the x vector and this is going to be the right hand side vector. So, Ax equal to b. So, the coefficient of x1 is sigma x1, this one. The coefficient of a2 is sigma x2I. So, that is over here, right. So, a naught a1 a2 and the right hand side is summation of yi. So, that is over here. So, similarly, the other 2 equations we can write, the coefficient of a naught is this, coefficient of a1 is this, coefficient of a2 is this. So, those things will go into the coefficient matrix, and similarly the third equation, these 3 values can go into the coefficient matrix, and this right hand side is given over here, right. So, just like in the last in linear regression, we had a nonlinear optimization problem, right, because it involved the square term in the objective function, that when we applied stationary condition last time we got 2 equations in 2 unknowns. In this case multilinear regression we did the same thing, we applied the stationary condition. When we apply the stationary condition, since there are 3 unknowns a naught, a1, a2, we get 3 equations in 3 unknowns. All the equations are linear, which can again be put in the standard format Ax equal to b. So, this part shows what we have discussed so far, right. So, we had this was our model, this is the measured value, this is the error. Our objective function was SR is equal to sum of square of error. So, this was EI, so square and then summation, right. And then we applied the 3 stationary conditions, dou SR by dou A naught equal to 0, dou SR by dou A1 is equal to 0 and dou SR by dou A2 equal to 0, and we got these 3 equations, 3 linear equations in 3 unknowns, which can be put in this conventional form Ax equal to b. Let us assume that if there were more independent variables instead of 2 independent variables, if there had been m independent variables, right. Let us say this was our model, a naught plus a1 x1I plus a2 x2I plus all the other terms till am xm xmi plus an error. Remember, this is the model, right. This is the observed data point or the measured data point. So, there may be some mismatch between what we have observed and what our model is capturing. So, we have this error. So, again this is the this is the same as sum of square of errors. This is the model part, this is the measured value. So, the error with respect to each data point, squaring it up and summing it up. So, this is our SR. So, over here if we are to apply stationary condition, we need to do dou SR by dou A naught equal to 0, dou SR by dou A1 equal to 0, dou SR by dou A2 is equal to 0, all the way up to dou SR by dou AM equal to 0, right. So, if we do that, so for example, if we do with respect to A naught, so this is dou SR by dou A naught equal to 0, this equation corresponds to that. So, it will be A naught into n plus A1 summation of x1I plus a2 summation of x2I all the way up to am summation of xmi equal to sigma yi. So, you can see the analogy between this equation and this equation, right. So, this equation it said like the first term is n into a naught, the second term is summation of the first independent variable, the second one is summation of the second independent variable, and the right hand side is summation of the dependent variable. So, over here also the right hand side is summation of the dependent variable, n into a naught is the same, right, and this summation of all these summations are the sum of individual independent variable and multiplied by their corresponding coefficient, right. So, similarly you can do dou SR by dou A1 equal to 0, dou SR by dou A2 is equal to 0, and you will be able to get these two expressions, and you can do all the way up to dou SR by dou AM equal to 0, right. So, in this case you will get A naught summation of xmi plus A1 summation of x1I xmi plus A2 summation of x2I xmi plus I mean the other terms plus AM summation of xmi the whole square is equal to summation of yi xmi, right. So, this equation again this set of equations. So, here we will have m equations, right. So, here here we had 3 terms, 3 unknowns a naught, a1, a2, right. So, here we will get 3 coefficients, here we have m plus 1 coefficients, right, m plus 1 because we are starting with a naught, right, a1 to am are m coefficients, and then we have this a naught. So, we will have m plus 1 coefficients. So, here also we will have m plus 1 equations. So, just like we formed this matrix, just like we put this normal equations, right, into this matrix form, these normal equations can also be put into this matrix form. So, now if you see there is actually a symmetry over here, right. So, if we know how to do for 2 independent variables, we can do it for m independent variables, right. So, now let us look at an example. So, in this case we have been given 6 data points, right, we have been given x1 and x2. So, x1 is one dependent variable, x1 is one independent variable, x2 is the other independent variable, and y is the dependent variable. So, these values are given and we have established this. Now, our task is to find out these individual values and then we need to solve it, right. So, in this case n is 6. So, summation of x1 is 4, summation of x2 is 18, summation of y is 104, summation of x1 square. Remember again it is not 4 square, right, it is each element has to be squared and then their sum has to be taken, right. So, it is 6, summation of x1 I x2 I is x1 into x2 0 into 0, 0 into 2, 1 into 2, 2 into 4, 0 into 4, 1 into 6, right, and then we need to sum it up, right. So, the 16 will go in these 2 places, and then we have this yi x1I. So, that is 14 into 0 is 0, 21 into 0 is 0, 11 into 1 11, 12 into 24, 12 into 2 24, and similarly you can calculate. So, that summation happens to be 58, and then we will require x2 square over here. So, each element of x2 has to be squared. So, we have 6 over here. So, 6 square is 36, and then we need to sum this. Remember again it is not 18 square, we need to sum this vector, right. So, that is 76. Similarly, we will have to calculate x2 into y. So, in that case it is 14 into 0, so 0, 21 into 2, 42, and similarly we can calculate the other values, and that summation would be 342. So, now we have all the values. If we plug them, these are our 3 equations in 3 unknowns, 3 linear equations in 3 unknowns. So, if we solve this, we get these coefficients. A naught is equal to 14.02, A1 is equal to minus 6.44, and A2 is equal to 2.53. So, our model is y is equal to A naught, so 14.02 plus A1 which is minus 6.44 x1 plus A2 x2 is 2.53 into x2, right. So, given any other value, so for example, if we say at x1 is equal to 3.2 and x2 is equal to let us say 4.5 8, right. We do not know the value of y from this data set, right, but if we can plug these values 3.2 and 4.8 into x1 x2 and we will be able to calculate y. So, that is the benefit of having a model. Now that we have calculated the model, right, we can also use the same concept coefficient of determination which we discussed earlier for multiple linear regression, right. It is valid over here also. Right. So, these three definitions we already know, right. We know the model over here, the model coefficients over here and the model is given over here. So, now from the model, from these value we can calculate these values. So, for example, this 24.14 is y is equal to a naught is 14.02 plus a1 is minus 6.44 into x1, x1 in this case happens to be 1 plus a2 that is 2.53 into x2. So, x2 is 6. So, if we calculate these values we will get 22.76. So, for 24.14 we should have used x1 is equal to 0 and x2 is equal to 4 in this equation and we would have obtained y model, right. So, for determining this y model we will not require this y, right. So, this is the value predicted by the model, right. So, the error we can find out, right. So, the mean of y in this case is 17.33. So, y minus y mean. So, again 14 minus 17.33 the whole square will be 11.09, 21 minus 17.33 the whole square is 13.47 and this can be calculated, and then if we sum this is nothing but the definition of ST. Similarly, we can calculate model, right. So, here since we are showing you only 2 decimal you do not see a value over here, but there is a difference over here, right. 14 minus 14.02 the whole square, 21 minus 19.08 the whole square and similarly, right. So, this happens to be 8.29. So, here itself we can say if we had considered the model to be nothing but the mean, this is the error, and over here if we consider the model with these coefficients then this is the residual error. So, we can calculate r square over here. So, if we plug in these values ST value, SR values in this we get a r square of 0.95. So far what we considered is like, so multiple linear regression, if we are to summarize, we started with 2 independent variables, then we extended it for m independent variables, right. In both the cases we had constant a naught, right. The first time we had a naught plus a1 x1 plus a2 x2, the second time we had a naught plus a1 x1 plus a2 x2 plus a3 x3 all the way up to am xm, and then we looked into an example as to how to exactly calculate the coefficient values and the coefficient of determination, right. Now, we will see like what if the model did not have a constant coefficient. So, model is not y is equal to a naught plus a1 x1 plus a2 x2, but my model is y is equal to a1 x1 plus a2 x2, right. So, let us look into that. Right. So, this is what we have previously derived, right. So, this was our model, this is our model, right. This is what is the measured value. So, the error is E, and then we said y minus the model, right, that is error, right, with respect to the ith point, square it up and sum it up. So, that is nothing but sum of square of residuals, and we had this m plus 1 equations due to the stationary condition. There are m plus 1 unknowns. We applied the stationary conditions and determined this m plus 1 equations, right. And then we just plug and then just we put it in the conventional format Ax equal to b, because all these equations are linear, right. So, this is the coefficient matrix given a data set, this can be completely determined, this can be completely determined. So, the only unknown is this x or this coefficients of the model. So, that can be calculated if we know how to solve linear equations, right. So, now the case is what happens if there is a no constant. So, if there is no constant, let us say if the model does not have this a naught, right, everything remains the same, right. So, this a naught is not there. So, now we have so the definition of SR is still the same, right, yi minus the model without a naught, right. So, this a naught is what is not here. So, without constant coefficient, right. So, y minus this model
right, yi minus the value obtained from the model, ei, square it up and sum it for all the n data points, right. So, that is the same thing, right. In this case, now we need to differentiate only m times dou sr by dou a1, dou sr by dou a2, dou sr by dou a3 all the way up to dou sr by dou am and equate it to 0. Right. There is no dou sr by dou a naught, right. This cannot be determined because the model does not have a naught, right. So, now we have m equations, right. So, similarly if you put them in the conventional format, all these equations would be linear, nothing changes, right. All these equations are linear with respect to a1, a2 and the coefficient model coefficients all the way up to am. So, this is again in that format ax equal to b, right. So, here we had m plus 1 equation, here we will have m linear equation, here it was m plus 1 linear equation, here it is m linear equation, right. So, here if we see, it is nothing but whatever we derived for the constant coefficient except for this row and for this column, right. So, all the other terms would be the same, right. So, that is how we can still work without constant coefficient, right. If the model does not have a constant coefficient, still we can apply the same concepts which we have discussed so far to fit those kinds of model. So, that was multiple linear regression, right. Now, we will move on to polynomial regression, where we still have only one wherein we have one independent variable and one dependent variable, but the model is polynomial with respect to the independent variable, right. So, for example, if the data set is like this, we might choose to fit a polynomial model, let us say a cubic polynomial model rather than a straight line, right. So, remember in regression you need to know the data points, right, and you need to know the model, right. If you do not know the model, there is you cannot even apply regression. So, the nature of the model should be known, right, only the coefficients are unknown. So, for example, if you give some data points and ask a model to be fit to it, the first question is what is the type of model, right, whether you want a linear model or a non-linear model. So, that has to be first fixed. Only when you fix the model can we attempt to determine the coefficients of the model. So, regression requires the data points as well as a model. Now, if you do not know the model, you might choose to fit 2 or 3 different models and see whichever model best represents your data, you might choose to take that as the final model, but to apply regression you require a model, right. So, this is the model, right. So, a naught plus a1 x plus a2 x square all the way it can go up to am x power m. So, here also there are m plus 1 unknowns, right. This is the measured value or the observed value, this is what is from the model, right. So, there could be a difference between the measured value and the model. So, that is the error, right. So, this is the compactly it can be written like this, right, a naught plus sigma j is equal to 1 to m, because there are these m terms aj x power j plus the error, right. So, this is the generic polynomial regression, right, but first we will work with y model is equal to a naught plus a1 x plus a2 x square. Similar to regression, multiple regression, wherein we started with just x1 and x2 and then extended to xm, we will do the same thing over here, that we will start with just a naught, a1 and a2 and then we will extend it all the way up to am, right. So, by now you should be familiar with this, right. So, this is yi is the observed value, this is what we get from the model, right. The minus sign is because yi minus y model, right. So, all these positives over here, all these positives over here would become negative, right. So, the error is the observed data point minus model the whole square, right. So, the error square. So, what we are going to do is the same thing, that we are going to minimize the sum of square of errors I is equal to 1 to n ei square, right. So, error in this case is yi minus this model, right. So, for the sake of completeness we will do it, but otherwise you should be able to do it by yourself, right. So, it is just that now we need to again apply the stationary points, right. Dou sr by dou a naught equal to 0, dou sr by dou a1 is equal to 0 and dou sr by dou a2 is equal to 0, right. So, dou SR by dou A1 equal to 0, the same thing 2 times this x, so x square 2 times this expression, right, and when we differentiate A naught minus A naught with respect to A naught, we get a minus sign. So, that is why this minus sign is over here. So, that has to be equated to 0, and then again do the usual rearrangement. Here we again have the term sigma yi, right, which is completely known, that can be taken to the right hand side. Otherwise these A naught, A1, A2 are unknown, right, all the other terms are known. N is the total number of data points, right. So, similarly we need to calculate dou SR by dou A1 is equal to 0. So, 2 times this entire expression. So, differentiation of yi with respect to A1 would be 0, A naught would be 0, over here we will get a minus xi, right. So, that minus can be written over here. So, minus 2 times xi this expression, and then xi can be multiplied, and this term if you see, it can be taken to the right hand side because it is completely known. Again this term and this term are known because the data points are known. So, we can calculate it. The only 3 unknowns are A naught, A1 and A2, right. So, that this is the second equation, and the third equation is dou SR by dou A2 is equal to 0. Again the same concept we need to apply, right. So, xi square, since it is differentiation with respect to A2, this xi square is a constant, and because of this minus sign appears over here, right. And then over here this term would be completely known because you have x and y, right. So, you can calculate x square y. So, square each element of x, multiply it with y, and then sum it up over here, right. So, this term is known, so that can be taken to the right hand side. Otherwise again A naught, A1, A2 are the unknowns, A naught, A1, A2 are the unknowns, and these coefficients can be determined, right. So, these are the 3 normal equations in this case, right. Again they can be put into conventional Ax equal to b form, right. So, these 3 things are completely known. So, that will form our b vector, and this n sigma xi square are known, all these terms are known. So, they would come in the coefficient matrix, right. So, if we know how to solve this, then we can know given data points, if we know how to solve this, we can find out A naught, A1, A2, right. So, in all the 3 cases, right, in linear regression, multiple linear regression and polynomial regression, if you see the coefficient matrix, it would be symmetric, right. So, sigma xi, sigma xi square, sigma xi cube, sigma xi cube, right. So, this is the diagonal. So, it will be symmetric. This matrix will also be positive definite, and there are better methods to solve this Ax equal to b, efficient methods to solve this Ax equal to b. So, what we currently saw was A naught plus A1 xi plus A2 xi square. So, we restricted to only the quadratic term, right. So, this is nothing but the error square, sum of square of errors, and these were the 3 equations we obtained because there are 3 coefficients which we do not know, A naught, A1, A2. So, these were our normal equations, right, and that can be put in this Ax equal to b form, and this A is again positive symmetric positive definite, right. So, what if we did not, what if we had more terms, right. So, let us say A1 x1 plus A2, for example, if we had y is equal to A naught plus A1 x plus A2 x square plus A3 x cube all the way up to am xm, right. So, this is model, right. So, if this is the observed value, then we also have the error. So, what if our model is this one? So, conceptually everything remains the same, it is just the math that we will have to do, right. So, in this case it is y minus y model, right. So, that is the error square. So, again we need to minimize this. To minimize this, we need to apply the stationary conditions, right. So, the stationary conditions here again it would be m plus 1 equations, right, because remember we have m constant coefficients from 1 to m, and then we also have this A naught, right. So, right now we are not talking about without constant coefficient, we are only talking about higher order polynomial terms being present in the model. So, we can derive this m plus 1 equations, right. So, it is the same thing, dou SR by dou A naught equal to 0, dou SR by dou A1 equal to 0, dou SR by dou A2 equal to 0, all the way up to dou SR by dou M equal to 0. So, these will be our m plus 1 normal equation. Again they can be put in the standard Ax equal to b form, because all these m plus 1 equations are linear. So, now let us look at an example for polynomial regression, right. So, these are our data points, we have 6 data points, right, and these are our 3 normal equations. So, the model involves only till the square term y is equal to a naught plus a1 x plus a2 x square. So, the number of data points is 6, summation of x is required, which is 15, summation of x square is required, again it is not 15 into 15, right, it is each element has to be squared and then it has to be summed up. So, that will be required in these 3 places. We require summation of y, which is 152.6, then we will require summation of x cube, we need to calculate this and the summation of it is 225, and then we will require y into x. So, y into x is again not 15 into 152.6, right, it is 0 into 2.1, 1 into 7.7, 2 into 13.6, 3 into 27.2, and then this has to be summed up, right. So, that comes out to be 585.6, x power 4, again this to the power 4, and this summation happens to be 979, which will be required over here, right. Then we require x square. So, x square is over here, y is over here. So, 0 into 2.1 0, 7.7 into 1 7.7, 136 into 4 54.4, 27.2 into 9 244.8, and then we need to sum this vector. So, that will be 2488.8. So, if we plug in those values and solve for these 3 equations in 3 unknowns, we will get 2.48, 2.36 and 1.86. So, our model is y is equal to 2.48 plus 2.36 x plus 1.86 x square, right. For x is equal to 3.5, we do not have the value of y. So, but that can be plugged over here, x is equal to 3.5 can be plugged into this expression and we can find out what is the value of y, right. And if we are interested, we can also find out dy by dx. So, that will tell us the behavior of y with respect to change in x, and we can also calculate d square y by dx square. And if there are any inferences, so for example, this x and y is going to be some physical variable, right. So, these can give additional insights. So, once we have this model, we can calculate these values dy by dx and d square y by dx square. So, the coefficient of determination is the same concept, right. So, we have this observed value, we know the model value, right. We can calculate the model value because we know the constant coefficient, right. So, for example, this 26.30 is going to be 2.48 plus 2.36 into 3 plus 1.86 into 3 square because of this model, right. So, that will be 26.30. So, that is how we calculate y model, and then we know the mean of y can be calculated, which is 25.43. So, this terms can be calculated, y minus y mean the whole square can be calculated. So, that works out to be 2513.39. Similarly, y minus y model, right, y minus y model is so for example 13.6 minus 14.64, the whole square would be 1.08 and the summation would be 3.74. From here itself we can see that ST minus SR is significant, right. So, we have so the model coefficients which we determined are actually better than considering the mean itself as model. So, R square in this case should turn out to be very good, right. So, if we plug in these values in this expression ST minus SR by ST, we get an R square as 0.99, right. So, we have these data points, right, and now we have this coefficient. So, between 0 and 5 we can generate, let us say 1000 2000 points, and then we can plug in the model because the model is fully known. Once A0, A1, A2 is known, if we plug various values of x, we get various values of y. With respect to that, we can actually plot the entire model in this range, right. So, given any value of x between 0 and 5, we will be able to predict the value of y. So, that is the use of regression. So, to consolidate whatever we have seen so far, right, what we need to do is define the objective function, right. In this case, the objective function was sum of square of errors, right, or sum of square of residuals, which is nothing but the error or residual is nothing but the difference between the observed value and what the model would predict, right. So, that has to be minimized. So, in order to minimize that, we apply the stationary condition. So, in linear regression, in simple linear regression, wherein there were only two coefficients a0 and a1, because the model was a0 plus a1x, we found out dou SR by dou a0, we equated dou SR by dou a0 and dou SR by dou a1 to be 0, we equated it to 0. So, we got the normal equations, and the normal equations were linear. We had two unknown coefficients a0 and a1 and two linear equations. So, we were able to find them out. The same concept we applied in multiple linear regression and polynomial regression. We framed the objective function, which is nothing but minimization of sum of square of error, and then we applied the condition for stationary, we determined the stationary points, and that led us to the number of that led us to the normal equations, right. So, in all the three cases, whether it is with constant coefficient or without constant coefficient, we ended up with set of simultaneous linear equations, right. So, that was the whole concept, right. We kept applying it multiple times to make sure you get the concept. All these three cases, simple linear regression, multiple linear regression and polynomial regression, can be fit into something called as general least square regression. So, now we will look into that, right. So, for example, all those three models are a subset of this particular model, y is equal to a0 z0 plus a1 z1 plus a2 z2 all the way up to am zm plus e, right. So, this part constitutes the model, right. So, the value predicted by the model plus error would be the measured value. So, if this were to for this to fit into linear simple linear regression, this z0 is 1, z1 is x1, right. So, this z2 onwards, z2 to zm is 0. So, in that case, this reduces to simple linear regression, right. For multiple linear regression, z0 is again 1, because we have this, we want this constant coefficient, z1 is x1, z2 is x2, and similarly zm is xm, right. So, this is what we solved. So, if we can solve this one, if we have a generic expression for this one, that would be valid for this one also, right. So, under the condition z0 is 1, z1 is x1, z2 is x2 and zm is xm, all the way up to zm is equal to xm. And similarly, polynomial regression can also be represented by this one, with z0 equal to 1, z1 is equal to x, right, and then we require x square over here. So, z2 is equal to x square all the way up to zm is equal to xm. So, this is the model which we worked with, right. This was the model part and this was the error, right, and this is the observed value. So, all these three cases which we saw is actually a subset of this general linear least square. So, even it can capture, even we can fit models like this, right, y is equal to a0 plus a1 sin omega t plus a2 cos omega t plus error. Again, this is the model part, this is the error part, this is the observed value, right. So, here for this model to be represented by this, z0 has to be 1, right, because here we do not have any coefficient. So, it has to be 1, z1 is sin omega t, right, and z2 is cos omega t, right. If we take z2 as cos omega t, this model, this general model boils down to this model. So, what I am trying to tell you is that all these three cases which we independently discussed, right, or cases like this can be solved if we are able to solve this one, right. So, this is the once we are able to solve this one, all the cases can be deduced from that. So, let us see. So, this is that general model which we discussed in the previous slide, right. So, if n data points are given and if there are m variables, right, let us say we will have let us say for this the data point is going to be y1, y2 all the way up to yn, and then we are going to have here if you see z0, z1, z2 all the way up to zm are the m plus m independent variables, right. So, here we will have z0. So, this is going to be z01, z02 all the way up to z0n. Then we are going to have z1, right. So, this is z11, this is z12 all the way up to z1n, and then let us say z2. So, z2 is the variable, the first point of the z2 variable, the second point of the z2 variable, and the nth point of the z2 variable. Similarly, we can extend it to m variables. So, this is given, either this is given or this can be obtained from whatever data is given, right. So, these are our equation, these are our data points, right. So, if we are to apply this model to each of this point, so these are the n equations which we are actually specifying. So, y1 is equal to a0 z01 plus a1 z11 plus a2 z21 all the way up to am zm1, right. So, this is again the model part, and there may be some error associated with the model for especially for the first point. So, that we indicate E1, right. And for the second point, if we apply the model, right, this is the value obtained from the model. So, that is, and the error need not be the same as the error for point 1. So, remember the first slide wherein the error associated with each point was different, right. So, that is why this error is being separately written for each of the n points, right. So, these are the observed values, this is what is we are getting from the model for each of the value by substituting the point, right. So, z2 is the variable, when we say z21 that means we have substituted the first point, when we say z2n that means we have substituted the nth point in the model, right. So, this is the model part and this is the error vector, right. So, these n equations can be written in this matrix form, b is equal to ax plus e, right. So, a from this one if you see it is nothing but this coefficient matrix, right, which is nothing but this data points. So, that is what is a, right, and this y vector is nothing but the observed points, right. These are the unknown coefficients m plus 1 coefficients because we are starting with a0, plus we have this error vector, right. So, this can be compactly written as the vector y, the z matrix, the vector a plus the error vector, right. So, this a is lowercase a, right. So, this set of equations can be represented by this, right. So, this is what is our regression, this is what is our problem, right. So, now our job is to find out this a from this, right, and we do not know the error. So, this is a analytical solution, right, this can be solved, and the solution to this is z transpose z into a is equal to z transpose y. So, if you are interested in how did this derivation happen, how did we get this analytical expression, you can look into this book by Matthews and Finks, right. This derivation is given there. So, for this problem instead of finding out all the derivatives and stuff, if we solve this set of equations. So, this if you see it is linear equations in which z is known, right, this is the z is known. So, z transpose z is also known, a is what we are trying to find out, right, and y is known. So, this is y and z is again known. So, z transpose y can be calculated, right, and z transpose z can be calculated, right. So, we directly get this as a, this as b, x, right. So, if we use this analytical expression we do not need to find out the summation of each. If you remember we solved lot of calculations to actually find the coefficient matrix and the right hand side vector. So, all that can be avoided, right, if we make use of this analytical expression, right. In view of the nature of this course we are not showing you the derivation, but you can have a look at the derivation. Now that we have looked into general linear least squares, right, we will let us use the concept which we learnt just now, general linear least square, to solve the multiple linear
regression problem which we have solved earlier, right. So, this is the problem which we have solved earlier, right. So, x1 is an independent variable, x2 is an independent variable. We have 1, 2, 3, 4, 5, 6 data points, right. And this is the model which we had to fit. Y is equal to a naught plus a1 x1 plus a2 x2, right. So, for that if you go back and look at all the derivation and the matrix which we obtained, this was the coefficient matrix, this is the right hand side vector. When we substitute these values, right. So, all that we have done previously, so we are not repeating it over here, right. So, but if you calculate all of this, you will get this coefficient matrix and this right hand side vector, which can be solved to obtain this coefficient, these coefficients, right. So, that is what we have done previously, right. So, now that we know general linear least square, for general linear least square, this is our model, right. So, in the previous few slides we have seen this is the model, and the solution to this is this Z transpose Z into A is equal to Z transpose Y, where Z matrix is given by Y. This Y vector is nothing but the dependent variable, right. So, that is something that we are always going to get from the data points, right. Over here the Z matrix is Z naught. So, the variable Z naught, the first point, right. So, this entire column is the variable Z naught and the endpoints. This entire column is the variable Z1 and the endpoints. Similarly, this Zm is the mth variable, all the endpoints. So, that has to be if we stack that in this form, that will be our Z matrix. So, once we have this Z matrix, we can merely compute Z transpose Z, that will be our coefficient matrix. This coefficient matrix will be equal to whatever we obtain over here, right. And the right hand side vector also same. If we do Z transpose Y, Y is a vector, column vector which is known to us, and Z is this matrix. So, if we do Z transpose Y, we will get a column vector. That column vector will be the same as this right hand side B vector. So, rather than computing this all this terms, so for example, rather than computing this, we will be directly using this analytical solution to solve the problem which you are currently seeing, right. So, the current model that we have is, so this is our data point, right. So, whenever we have data point, we write the model and then we write the error term, right. But if you are merely writing the model, then we do not include the error term, right. So, right now it is the data point which is observed equal to model plus some error that might be there, right. So, for this to be equal to this expression, the current problem to be equal to this, we need to take Z naught as 1, Z1 as x1 and Z2 as x2, right. So, if we take that, our current problem is a general linear least square model, then our Z matrix is a column of ones, right, and the x1 variable stacked, all the endpoints stacked as the second column, the second variable stacked, all the endpoints stacked as the third column, right. So, that will be our Z matrix. So, here if we apply the same thing to our current problem, so Z matrix in this case is a column of 1, because we have this constant coefficient. Had we not had this constant coefficient, we do not need to include this column of 1s, right, and then we just need to stack these two columns x1 and x2, right. So, the way we have stacked is the constant, the first variable and the second variable, right. So, the solution which we will get will also be of the same form, that the first value that we get will be a naught, the second value will be a1, and then we will get the final coefficient a2. So, if this is Z, obviously this will be Z transpose. So, if you multiply Z transpose Z, we will get a 3 cross 3 matrix, and that 3 cross 3 matrix will be exactly similar to what we have got here, right. So, these two matrices are similar. So, without computing all these terms over here, right, we can directly get by doing Z transpose Z, right. Similarly, the right hand side vector, instead of computing this, right, we can merely do Z transpose Y, right. So, Y is the set of values which we have got for the dependent variable. So, if we do Z transpose Y, again we will get a 3 rows 1 column, a column vector, and this value will be similar to what we have over here. So, since the coefficient matrix A and the right hand side vector B are identical, our solution X will also be identical, right. So, instead of employing this approach, right, we can directly employ this approach to solve a linear least square problem. Again it is one and the same thing, it is just that this might be a little bit more convenient.
Right. So, once we do that, we can calculate the R square, right. Once model is known, then it is the same thing, y minus y mean the whole square, y minus y model the whole square, and then sum it up, right, and then plug it into this expression, that will give us the R square value.
So, now let us look into a problem, right, which we have previously solved without constant coefficient. Remember, previously we had fit a model where there was constant coefficient, and we also had fit a model where there was no constant coefficient, right. So, with constant coefficient we have seen how we can apply general linear least squares, right. So, without constant coefficient it is going to be similar, right. For the sake of completeness, we will just show you the calculation. This is the problem which we had previously, right. So, x1, x2, y. This time we have a model wherein there is no constant coefficient, there is no a naught, right, there is no constant coefficient, right. So, in this case our model was y is equal to a1 x1 plus a2 x2, right. Our task was to find out a1 and a2, the values of a and a2 such that this model best fits this data point, right. So, if you do dou SR by dou a1, dou SR by dou a2 and equate to them to 0, you will get two linear equations in two unknowns a1 and a2, and if you write them in the conventional Ax equal to b form, this is what we will be getting. So, the matrix which we got is this one, this is the A matrix, this is the right hand side vector, right, and this was the solution, right. So, now let us do the same problem using the general linear least square model. So, again as we discussed in the previous slide, this is our model, this is the analytical solution of that model, and in this analytical solution the Z matrix is the Z naught variable, the Z1 variable all the way up to Zm variable stacked one after the other and all the endpoints. So, that is our Z matrix. So, in this case our model is a naught x1 plus a1 x2, you can even say it is a1 x1 plus a2 x2, it is just the notations that are different. This is our model, this is the data point, and so this is the error term has to be over here, right. So, for this problem to be equivalent to this problem, Z naught has to be x1, right, because there is no constant coefficient term, right. If constant coefficient term had been there, then Z naught is equal to 1, here there is no constant coefficient and Z1 is nothing but the second variable x2, right. So, in this case this is going to be our Z matrix, right. So, for the current problem, the x1 column, all the 6 points have to be stacked over here. Similarly, the x2 variable has to be stacked over here. So, we get a 6 by 2 matrix, right. So, this is the Z transpose. So, once we do Z transpose Z, we will get a 2 cross 2 matrix, right, and again we can calculate Z transpose Y. So, if we calculate Z transpose Y, we will get this right hand side vector, right. So, now if you see, this is exactly identical, this A and B is identical to what we obtained over here, right. So, solution would be the same, a naught is equal to 1.11 plus a1 is equal to 4.23, right. So, a1 is equal to 4.23. So, that completes multilinear regression with constant coefficient and multilinear regression without constant coefficient, in terms of general linear least squares. Without general linear least squares also we have seen how to get that. Now, we have seen if we know the analytical solution for general linear least squares, we can directly employ that for multiple linear regression problem, right. And similarly, this can be extended for polynomial regression also, because polynomial regression at the end of the day we are converting into a multiple linear regression problem, right. So, whatever we have discussed for multiple linear regression with the analytical solution of general linear least square is also valid for polynomial regression.
So, again this is just for the sake of completion, you can calculate the R square value, right. So, model is known, you can calculate how the model, had we taken the mean as the model, what would be the error, and now that we have a model, what is the error, right. So, the difference St minus Sr shows the improvement, St minus Sr by St is the coefficient of determination, right. So, that is 0.94 in this case. That concludes the linear regression part, right. So, now we look into nonlinear regressions. So, linear regressions, it boils down to solving a set of simultaneous linear equations. Either we can do it as we did in the first part of this session, or we can use the analytical expression Z transpose Z into A is equal to Z transpose Y.